There you go.
No, the thing was just in the way. Okay. Hello, everyone. I am Lisa Tapper. I go to St. Catherine University. And we have been working with the U of M and University of Minnesota Morris, so Twin Cities and Minnesota Morris, on this high altitude ballooning project for neutron detection in the stratosphere. All right, so we begin with high altitude balloons, and this is what a stack looks like. And then inside we have our payloads. So we put different sensors in there and they collect data as they go up into the stratosphere. And then the balloons burst, they come down and we get the data typically off of SD cards. And then load those into Excel and just look at the data. We also use GoPros to do this specific project. And I will get to that, but then we watch the video. So our main layer that we're looking at is in the stratosphere. We really take data from like the ground up to about 100,000 feet is where it usually ends. At least that's where our balloons typically burst, and they're all filled with helium, but we're looking mainly between the tropopause and the stratosphere. And the tropopause is interesting because then we see different effects like low temperature, low pressure. So we can see that in our data as well, which is cool. And here's what a typical balloon flight looks like. So we start with the ascent, and then we have the Regner phosphor maximum labeled, or the RP max, which I'll get to in the next couple slides. And then you can see in the middle, middle image, the balloon bursts, and then it'll come down. And so we have a parachute attached so we can it comes down safely for the most part. And what we're looking at is particles. So we're looking at galactic cosmic rays colliding with the Earth's atmosphere. And this results in high energy secondary particle that come down in like showers, so cosmic ray showers. And we are looking on the right side of the image, so the mesonic component. So like pions and muons is typically what we are looking at. And this interaction layer happens between 15 and 25 kilometers. And that was actually found from doing studies underwater and seeing a similar thing. And then they were like, okay, let's try it in the atmosphere. And so we found they found a similar thing. And now we're looking at that through all of our research. And these are the two men who actually discovered this. So Eric Regner and George Foxford. So they started with their underwater measurements and then found the RP max and related that to the atmosphere. And so now that is our main interaction layer, and we are hypothesizing that that we will see the most interactions in that layer. So what we're looking at is the particles undergoing alpha decay as they go through this interaction layer, and kind of just seeing if our hypothesis is true, and then in the future quantifying that and saying like, okay, was this a pion or was this a muon? And then we can actually determine where we see the most intensity of energy that is released. And so how we do this for our charged particles is we use, with our neutron experiment, we do the omnidirectional. So we have, you can see this in our exhibit, but we have these tubes that are contained in like a rectangular casing, and they will get counts from every single direction. So we use those in conjunction with the neutron. And then we have a separate one that flies in a separate stack or a separate box that does horizontal and vertical counts. So we can compare, are we seeing more scattering vertically or horizontally? And that is our quad configuration. And then how we do the neutron measurement specifically is we use a personal neutron dosimeter, and it's it has a polymer of Freon 12 within it, and so that is really good for the fast neutrons going through the atmosphere, and it'll actually create a bubble that we can see with the GoPro camera and also hear as well. And so they do have a pretty short lifetime, about 3 months. So we have to do it like, you know, within a certain period of time, but they do give us really good data. So we like them a lot. So what the PND does, it detects fast neutrons during the balloon flights. And we are specifically looking at elastic versus inelastic scattering. We can't quantify that yet, but I think we will in the future. But we do know that one of the two form occurs, and we can say that there was an interaction of this fast neutron in the atmosphere, and we can see it and quantify that with the neutron tube. And this is our neutron payload. So we have the neutron tube, the Pnd attached to the lid. And then we have our omnidirectional, which is like the yellowish, like cream box on the left side. And then our GoPro camera, which is in the, oh, okay, you can see the cursor. This is our GoPro camera that is looking at the neutron tube. And we have like very specific video settings for the GoPro. And we also have a light, and we seal the box very well. So there's no external light coming in. It's just the light from on the side of the box. And so just so we can see the neutron tube. And the University of Minnesota Morris started this. And then over the years, we started to collaborate with them. And now we've kind of taken it over, and we are just furthering that experiment. And so here's how we actually analyze the data. So we have all these GoPro videos, and we have to go through each of them like one by one. They come in 19-minute segments, but we watch them one by one, and we can see like the different colors mean either different videos, or is it video and or visual and audio, just audio, just visual. So we can kind of determine how many bubbles and then at what altitudes as well. So we have to do our altitudes separate and like extrapolate the data together, because the GoPro doesn't give us any altitude information. So here are our results. We do see, so the 15 to 25 kilometers is the RP max, and we do see a higher percentage of the bubbles in that range compared to below and above that. So our hypothesis has been confirmed. And then we can see how many bubbles we're actually getting by specific type. So we mainly see single bubbles. And this year we saw, or last year, we saw our first triple bubble formations, and it was all on the same flight. I think we saw 2 or 3, but that was pretty cool. And then here is the bubble counts overlaid with the charged particle counts. And so the altitude is on the y-axis. So this is like physically going up. But you can see that it's kind of hard to quantify, because the like 0 to 15 kilometer range is a lot bigger than the 15 to 25, but there are more counts for the blue, which is the charged, in that range compared to the other two. And then same with the neutron, the yellow neutron count as well. And so here is an actual bubble that did form. And I think I need help.
What's going on?
How do I go back?
Oh. Stop sharing it.
Okay.
Go back and share.
Yeah.
Somehow went into some goofy mode.
Okay.
All right.
I'm gonna try the video.
Oh, if you want to try the video, maybe the thing to do would be to go out of the presentation mode, and sometimes it does that, right? So
Actually, I'll just show the video if
Okay.
people have questions.
So if I click on this video thing.
Well, you might, oh, I think you-
Okay, that's probably what it is.
Okay,
I'm not happy about that. Okay. It's just-
that's okay.
Sharing. I'll create my own computer. There you go.
Okay, thank you. Okay. I am actually going to skip ahead, but our future plans include just quantifying our charged particle counts and using silicon photomultipliers to do that. And actually say what kind of particle it was, and then do this stuff in different formations. So right now, we've just been doing neutron tubes in one box, 1, 2, but now we could do multiple in one box, or we could have like a stack of 3 and do 1 in each box, just different formations. And we'll also be doing this during the 2023 and 2024 total or annular and total eclipses. So we will be flying all of these just to see how that varies. And I think this summer we will also be doing night flights just to see how it varies during the day and the night. All right. And I just want to thank Space Grant for allowing us to do this research. Okay. Questions?
What are your practical applications for this? Is this like a neutron flux thing, or is it like plasma physics?
Yeah, it's mainly flux and fluence that we're looking at. So those are mainly the practical applications, and just trying to understand more about the stratospheric layers.
Okay.
Yeah.
Could you put your graph of interactions versus night? Just curious.
This one?
Yeah, thanks. So with the, what height is that? Did it?
This is 30 kilometers, so about 100,000 feet.
All right, great.
Okay.
I actually have 2 questions.
Yeah.
So the first one I wanted to ask was, when you were talking about the inelastic versus elastic scattering of the neutrons, are you doing that via Raman spectroscopy, or am I thinking of a different thing? What instrumentation are you using for that? Or
Yeah,
do you want?
we haven't done any of that yet, but maybe this summer.
Okay. And then the second one I wanted to ask is, what was the significance between the single through quadruple bubbling that you were referring to earlier?
It's just what we see, and then we can say like, oh, they're actually 4 different particles going through the same, or we could see like, is it one that's going like this way and then like coming back. So it's just interesting to see, like, because a single one, we know it's just one going through, but for the other formations, we can see different effects.
The bubble detectors you're using, those just have like small liquid particles suspended in polymers. Is that what it is? So
Yeah.
it's like a vaporization of those from the neutron impact.
Yeah, so it just creates like a little bubble in there. Yeah.
So that's a lot of data from these flights. How many sort of events do you get per flight that you would do for that and like that?
For neutron bubbles, it ranges from like about 20 to 30, depending, but it's typically in that range. Any more questions?
Okay, I have one question. So you said it was hard to figure out when the images were taken because the GoPros are just kind of on their own. They're not really tied into anything. Did I understand correctly, or?
Yeah, we just have to, like on the GoPros, we can hear, like, we'll usually yell launch when we send the balloons up, and then we can hear when it bursts and then comes down and lands. So we usually try to correlate that way, but
So there's no active, you're not doing anything active where you're trying to correlate each frame on the GoPro with some sort of like time tag of your GPS receiver. You're not doing that. Okay. You want it.
Nice. We haven't gotten to that.
yeah.
Okay.
Done
we made more work for ourselves, so.
Oh, okay.
You said you could actually hear the bubbles forming too.
Yeah, we can. If anyone's interested in the video, I can show it at the exhibit.
Any remaining questions? Thanks, Anissa. So this